tricks. The chlor-alkali industry is a large worldwide multi-million industry. The basis of this industry is the electrolysis of sodium chloride solutions. The three products obtained from the chlor-alkali industry are hydrogen gas, chlorine gas with its yellowish-green color, and sodium hydroxide solution with the formula NaOH. Each of these products is used throughout the chemical industry to produce other products. Sibulelo and Legend had a closer look into the electrolysis reaction of sodium chloride solution, also known as brine. Let's see what they found.
And here's Legend to show us what new substances are formed when we apply electrolysis to ordinary table salt. I am pretty sure the results will surprise you.
Hi guys, before we start I have a question for you. Can you remember what salt's chemical name is? That's it, sodium chloride. In today's experiment we will be using salt. Valfos-based salt refiners is one of the companies that make the pure salt used by the local industries. Now it's time to see if we can use electricity to change sodium chloride into something different. We'll be using these to change this into chemicals, hopefully. First we must dissolve the salts in some water to make the ions mobile. This means that the sodium and chloride ions are free to move. Because some of the products we expect to form during this reaction are very alkaline and reactive, we'll use a universal indicator to help us see the changes that take place. Do you see that the indicator stays green? This tells us that the solution is neutral. To make sure that we can clearly see the changes which happen at each of the electrodes, we will separate the two halves of the experiment with cardboard. Cardboard works well because it lets the liquid through but keeps the products from mixing. It acts just like a salt bridge. All that's left to do is to put in the electrodes and to connect them to our battery. This will supply the potential difference we need. Now look closely at what happens as we leave the chemical reaction to run for a while. How cool is that? We definitely made some new chemicals during this process. Before the electrolysis of the salt solution, we had a neutral liquid. Now we have two new gases. We also made something that changed the pH of the solution. See, the indicator changed color from green to purple. Let's see if we can figure out what these chemicals are. At the positive electrode, a gas was produced. The color of the solution clearly turned from green to yellow, then the color faded away. The fact that the color fades away means that an oxidizing agent is produced here. There is also a very sharp smell that reminds me of bleach. This tells me that the gas is most likely chlorine. Now let's look at what happened at the negative electrode. At this electrode, a couple of things happened. Firstly, notice that a gas is produced. See how it quickly bubbles away from the reaction. I suspect that this gas is hydrogen. Can you think of a way we can test if this is true? You should remember that if a lighted splint makes a popping sound in the presence of a gas, it is a positive test for the presence of hydrogen. Do you see how the color of the universal indicator we added turned from green to purple? This means a substance that turned the neutral solution into an alkaline solution formed here. If you consider the reactants we used, you should expect this to be sodium hydroxide. Isn't it amazing how a simple thing like salt can be turned into three chemicals with very different qualities? Well, that's me. Sibo is going to show you how chemical industries use the process we looked at every day.
Thank you for showing us how electrolysis can cause chemicals to change, Legend. As you can imagine, when this process is used in the real world, it is done on a much larger scale than we do it in a lab. This is the NPC Chlorchem plant, and the people here take the electrolysis of salt very seriously. To ensure the best results, the salt they use has to be very pure, and a lot of effort goes into making sure it is. The salt is dissolved in water to make a saturated solution called brine. This is so that the salt can become conductive, allowing ions to move freely. The brine is then pumped into very large electrolytic cells, and this is where chemistry begins. A very large amount of energy is consumed by the process. The electricity supplied must be direct current and low voltage. This needs large transformers and electronics to work. The gases produced are stored in tanks and sold for many uses. We have already mentioned a couple of uses for these gases. Can you think of any more? Well, the hydrogen produced during the electrolysis of salt is used to make margarine from sunflower oil. The hydrogen adds molecules to the oil to make it spreadable. Another process that uses hydrogen is the Haber process. It turns nitrogen from the air into ammonia. The ammonia produced in this way can then be used to make fertilizers that make plants grow faster and produce better crops. Hydrogen combined with oxygen also powers the rockets that takes us to space. Remember the yellow-green chlorine gas that was produced? It is very poisonous and was even used as a chemical weapon during World War I. However, used by experts in controlled conditions, it can be made into many useful household products. For example, we find it in products that keep our swimming pools blue, our shirts white, and surfaces clean. Let's take a look at the last product that formed during the electrolysis of salt, sodium hydroxide. Sodium hydroxide is sometimes called caustic soda. It is a powerful chemical base and can be used to open up blocked drains. It is also known as lye, and when mixed with fat and oil, form the basis of the soap we use to wash.
Now we know what forms during the electrolysis of sodium chloride. Let's join Sibulelo to dig into what happens on a microscopic level in this cell.
The best place to begin to look at what possible reactions can occur, and to do that, we have to take a look at what is already in the mixture.
Right. The mixture is a solution of water and salt. We all know that salt is sodium chloride. So, I guess the chemical must be sodium chloride, NaCl, and H2O.
You're pretty close. Remember, we are working with a saturated solution of salt and water called brine. The sodium chloride breaks up into sodium cations and chloride and ions when it dissolves. You're right about the water though. You must never forget that the ions are dissolved in water, which means the water can react too. The best way to start your answer of any redox question is to circle the reactants on the table of standard reduction potentials. Next, we need to circle the products formed at the electrodes. We have hydrogen gas and chlorine gas. Remember that this reaction will not happen without added energy. Can you remember what we call this type of reaction that requires energy to start?
I do. Reactions that need energy to begin are called non-spontaneous reactions.
Well remembered, Nombulelo. A quick and easy way to tell a reaction is non-spontaneous is by drawing a line from one reactant to the other on the table. If the line slopes down from left to right with a negative gradient, the reaction is non-spontaneous. We know that the information we read from the table is accurate because the reaction we are examining, the electrolysis of salt, needs electricity to happen. We saw that when we did the experiment in the lab. The next step in solving a redox question is to write out the oxidation and reduction half reactions. This will also help us identify the anode and the cathode. Do you think you could write out these two half reactions correctly? I hope you started with the reactants we chose from the table earlier. The half reactions you wrote down should show that water reacts to produce hydrogen gas and hydroxide ions. The chloride ions react to form chlorine gas. Remember to write out the reactions in the order you found on the table, from the chosen reactants on the left across to the products on the right. You should be able to see that the water molecules are being reduced because 2 electrons are added here during the reaction. We say that water molecules are gaining electrons. Nombulelo, do you remember what this tells us?
I do. This tells us this is the cathode of the cell. There's that red cat again, which means that the chloride ions were oxidized at the anode. Right, Sibu?
That's right. You can see here that 2 chloride ions lost 2 to make a molecule of chlorine gas. Now all we need to do is make sure that the electrons are balanced and add the 2 half reactions together. We cancel out the electrons and add the chloride ions and water molecule on the left. The final ionic reaction will look like this. 2Cl- plus 2H2O goes to form Cl2 plus H2 plus OH minus.
Okay, I'm with you so far. But what about the sodium in the sodium chloride?
Well spotted, Nombulelo. The sodium cations in the reaction do not react at either cathode or the anode. We call ions that don't take part in a reaction spectator ions. This is because they are there, but only looking at the action, they do not take part in the reaction. As you see here, the reaction at the cathode produces hydroxide ions. These, combined with the sodium cations, will make the sodium hydroxide product we saw during our experiment.
Now that we know what happens on a microscopic level to the brine, we can look at the different types of electrolytic cells that are used in industry to produce the three products on a much larger scale. There are three main types of cells: the asbestos diaphragm cell, the mercury cathode cell. These two cells are not in use anymore because they pose a health risk due to the very poisonous asbestos in the diaphragm cell and equally poisonous mercury in the mercury cathode cell. The last type of cell is the membrane cell. It is the most modern but also the most expensive type of cell to produce. Sibulelo will tell us more about the membrane cell.
The design is very similar to the asbestos membrane cell, but engineers replaced the hazardous asbestos with a membrane of special plastic. In this cell, the brine is also pumped into the anode, just like with the asbestos membrane cell. But then it hits the very special part of this cell, the membrane. Scientists have developed a material that only allows positively charged ions to move across it. So this membrane does not allow the water or chloride ions to move through it. This is called a selectively permeable membrane. On the other side, in the cathode, fresh water is pumped in and then reduced to hydrogen gas. The rest of the water is used to remove the third product, pure sodium hydroxide. The salt must be very pure for this process, as the membrane can easily be blocked and is the most expensive part of this cell. The materials that are used to produce these incredible membranes are also so special that they are kept a secret by the companies that use them.
I certainly hope that this is a cell that most companies in the industry use today. It is the only one that doesn't pose a serious health risk to the chemical plant workers.
It is indeed, Nombulelo. It also produces the most pure and highest quality products. So though it is expensive to manufacture, it is economical in the long run.
Thank you, Sibulelo. This is a very interesting way of producing chlorine. But what is the effect on the environment? Chlorine gas is very toxic and should not be inhaled. The chlor-alkali plant should be built far away from residential areas, and the workers should also be very cautious. The caustic soda that is produced is also very corrosive and can cause chemical burns, and therefore it should not be allowed to seep into groundwater. And the hydrogen that is produced is very flammable when mixed with oxygen, so it is a big risk. The whole process uses a lot of electricity that also has a very negative effect on the environment. All of these should be considered before a chlorine plant is built in an area. Now you have seen how this cell works and the important product that is formed and the effect on the environment. See if you can do the question in the task video on this topic. You'll also find more information on our website at www.mindsearch.co.za/learn. Until next time, goodbye.